Welcome, space enthusiasts. Today, we're diving into a groundbreaking cosmic discovery. The James Webb Space Telescope, JWST, has captured a supernova distorted by a gravitational lens, revealing clues to a mystery that puzzled Hubble astronomers for years. How does a supernova get distorted? And why is this discovery so significant? Join us as we explore how JWST's incredible technology shed light on one of the universe's great mysteries. Why isn't the universe behaving the way it should? Or, to put it differently, why does the actual rate of cosmic expansion differ so wildly from what our theories predict? For years now, scientists have been wrestling with this mystery, known as the Hubble tension. But recently, the James Webb Space Telescope captured something astonishing, an image of a unique supernova appearing 3 times in the same shot. This visual trick is thanks to a phenomenon called gravitational lensing, and it provides us with an unprecedented opportunity to calculate the Hubble constant, the measurement that tells us how fast the universe is expanding. Yet, strangely, as this revolutionary technique delivers new data, it sometimes raises even more questions than it answers. It seems we may still be far from truly understanding the nature of the universe. And it's a reminder, even the greatest minds can miss a step. Albert Einstein, the genius behind the theory of relativity, once believed in a static, unchanging universe. He was so convinced of this that he introduced a cosmological constant to his equations to keep the universe from expanding or contracting. Then came Edwin Hubble, who observed galaxies racing away from us, and cosmologists Alexander Friedman and Georges Lemaître, who found expanding solutions in Einstein's own field equations. Our journey to understand the cosmos has always been full of twists and turns, and maybe the real revelation is that we're only just getting started. Einstein eventually had to let go of his idea of a cosmological constant, a term he added to his equations to preserve a static universe. He would later call it the biggest blunder of his life. Today, we know that the universe has been expanding ever since its beginning, a fundamental concept in astronomy. But here's where it gets interesting. The universe isn't expanding into anything. Instead, space itself is continuously growing. This expansion can be observed through distant objects in space, as the vast gaps between them keep stretching. When it comes to measuring the universe's current rate of expansion, the Hubble constant scientists have 2 very different methods. The first approach is based on the standard model of cosmology, which combines theoretical physics with data from the cosmic microwave background radiation. This relic radiation, a faint glow left over from about 380,000 years after the Big Bang, fills the entire universe even today. Using this method, scientists arrive at one value for the Hubble constant. But, as we'll see, another method gives us a totally different answer. The Hubble constant, which measures how fast galaxies are moving apart, comes out to around 67. But let's break down what that actually means. Its unit might seem strange: kilometers per second per megaparsec. For reference, a megaparsec is about 3.26 million light-years, and each light-year is roughly 9.46 trillion kilometers. So, this value tells us that galaxies drift apart at 67 kilometers per second faster for every 3.26 million light-years of distance between them. That's an impressive rate of around 244,000 kilometers per hour per megaparsec. But here's where things get complicated. That's just one way to measure the expansion. The other method involves observing celestial objects like Type 1, a supernovae stellar explosions that always reach the same brightness, and Cepheid variable stars, whose brightness changes predictably. With this approach, the Hubble constant jumps to over 73 kilometers per second per megaparsec, indicating that galaxies are moving 20,000 kilometers per hour faster than the first model suggests. So, if our universe is expanding faster than we expected, it raises a huge question: how could this be happening? This Hubble tension isn't just a minor detail, it's a mystery that's challenging everything we know about the cosmos. And the simplest answer might just be, Well, we don't have one yet. One easy explanation might be that past measurements were simply wrong. To see if we could really trust the data gathered by the Hubble Space Telescope, astrophysicist Adam Riess took a fresh look last year using the much more powerful James Webb Space Telescope. And if anyone can dig deep into the mystery of the universe's accelerated expansion, it's Adam Riess after all. He won the Nobel Prize in Physics in 2011 for this very work. Webb examined over 320 Cepheid variable stars, many of which had already been observed by Hubble. But instead of clearing things up, these new measurements only deepened the mystery. The brightness and distance data for these stars matched previous observations, once again suggesting a Hubble constant that significantly exceeds what theoretical models predict. Now we're faced with a startling problem. What happens when a constant isn't constant? How can we trust a value meant to describe the entire universe if it won't stay put? At this point, it almost feels like the cosmos itself is playing tricks on us. And Riess himself acknowledges that our current understanding may not be up to the task. Here's a more engaging version of your script. Our understanding of the universe might be anything but complete. There's a real possibility we've overlooked something fundamental in our cosmological models. Perhaps there are undiscovered particles or fields, maybe even exotic forms of dark energy or dark matter waiting to be found. This new supernova observation might be the key to unraveling the Hubble tension, an old mystery, but with a fresh approach. Scientists have now developed yet another method to dig into the mystery of the Hubble tension. And it all started with a surprisingly simple, yet profound question: what are these 3 points of light that weren't there before? Looking closely, experts identified 3 bright spots in James Webb's images of galaxy cluster PL CK-GON 165.7 plus 67.0 spots that hadn't appeared in Hubble's 2015 images. Soon, they realized they were seeing something extraordinary: one single supernova appearing in 3 places at once, thanks to a phenomenon known as gravitational lensing. In astronomy, gravitational lensing describes how light bends around massive objects, like galaxy clusters, creating multiple images of the same object. And in this case, the light from a distant supernova had been bent so perfectly by the mass of the galaxy cluster that we could see it in 3 different spots. In this case, light from a distant source, a supernova, gets warped by the gravity of another massive object positioned in front of it. For the observer, this gravitational lensing effect bends light rays, with stronger deflection occurring the closer the rays pass to the mass. Essentially, the gravity of a massive object acts like a cosmic magnifying glass, distorting and magnifying the light from structures behind it. But how did researchers realize they were looking at a supernova appearing in triplicate in the James Webb images? According to Brenda Fry from the University of Arizona, it all started with the galaxy cluster known as PLCK-GON 165. This region has a star formation rate of over 300 solar masses per year, a sign that also aligns with higher rates of supernovae. Sure enough, after further analysis, researchers confirmed their initial hunch. Webb had indeed captured the explosive death of a star. More specifically, we're witnessing the fiery end of a white dwarf in a Type 1a supernova. In this kind of event, a white dwarf star steals material from a nearby companion star until it reaches critical mass, triggering a spectacular explosion. These dazzling displays all start with about the same brightness and then fade at a similar rate over time, making them ideal standard candles for measuring cosmic distances. Standard candles like these are crucial for calculating the Hubble constant, the rate at which the universe expands. But this time, gravitational lensing brought researchers completely new insights. In this case, a cluster of galaxies acted as a gravitational lens, mirroring the middle image relative to the other 2. Essentially, the supernova's light traveled along 3 different paths to reach us. Since each path was a different length, and light moves at a constant speed, the explosion was captured at 3 slightly different moments in time. To illustrate this, Brenda Fry compares it to a triple vanity mirror, where we see three versions of the same person from slightly different angles. Imagine a sequence. In the right mirror, you see someone picking up a comb. In the left, they're combing their hair, and in the center, they're putting the comb down. Similarly, Webb's images reveal a time-lapse of the supernova, each mirror capturing a different stage of the explosion. But why does this deepen the Hubble tension? This time, lapse effect brings us one step closer to understanding the mystery, yet only seems to complicate it further. When we look closer, this triple supernova, complete with its time delays, distance, and gravitational lensing effects, offers an extraordinary opportunity for understanding the Hubble tension. It provides researchers with far more data than usual, sparking hope that we might finally get a clearer picture of the universe's puzzling expansion rate. In that spirit, scientists fittingly named this supernovas in Hope. With a redshift of 1.78, E's in Hope is one of the most distant Type 1a supernovae ever discovered. This stellar explosion happened around 10.3 billion years ago. But, in a sense, it's like an astronomical blind date. Multiple research groups under the HL program took on the task of analyzing SE in Hope for insights on the Hubble tension without any knowledge of each other's findings. The goal was to keep each team's analysis unbiased, so each subgroup worked in isolation and would reveal their results simultaneously on a designated day. When that moment finally came, the suspense was tangible. Teams gathered to present their findings, ready to see if their gravitational lensing data and calculations would align or deepen the mystery further. After analyzing the lensing models, researchers arrived at a Hubble constant value of 75.4 km/s per megaparsec, not quite 67, and not 73 either. So what does this tell us? On one hand, this result aligns with other measurements in the nearby universe. But on the other hand, it's still in conflict with values calculated for the younger universe. It's worth noting that this was only the second time the Hubble constant was measured with this method, and the first to use a standard candle. Yet, even this new measurement doesn't match the theoretical predictions. Right now, there's no clear explanation for this gap. Astronomers are hopeful, though. With more observations from the James Webb Telescope, they aim to sharpen their measurements even further. And if Webb's powerful lens can spot additional standard candles, we may finally solve the mystery of the Hubble tension. Gravitational lensing occurs when a massive object, like a galaxy or black hole, bends the light from objects behind it. This bending creates a magnifying effect, allowing us to see distant celestial bodies that would otherwise be hidden. Think of it like a cosmic magnifying glass, showing us glimpses into areas of space beyond direct reach. This process can distort the appearance of objects behind the lens, sometimes even creating multiple images of the same object. In the case of supernovae, gravitational lensing can stretch and magnify the explosive light, offering us rare and unique views of these powerful cosmic events. The James Webb Space Telescope is the most powerful telescope ever launched into space, far surpassing Hubble's capabilities. Its advanced technology includes infrared sensitivity, allowing it to detect celestial objects at incredible distances and observe them with a clarity never before achieved. This makes it possible to study phenomena like gravitational lensing in unprecedented detail. In this case, JWST was able to observe a supernova's light as it traveled through the gravitational field of a massive galaxy cluster, capturing details that Hubble could not see and helping scientists learn more about the nature of these events. So what's so special about this supernova? The light from this exploding star was distorted as it passed by a massive galaxy cluster on its way to us. This distortion is what made it visible to JWST and allowed astronomers to observe it in detail. Previously, Hubble had captured images of similar distortions but couldn't fully explain the underlying causes. Now, JWST's sharper imaging provides more data, helping to solve the mystery and enabling astronomers to identify the type and distance of the supernova, which was previously unknown. Years ago, Hubble observed similar gravitationally lensed images, leaving astronomers puzzled about their origins. With JWST's observations, scientists can now confirm that these distorted light patterns are from a distant supernova, lending new insights into the way gravitational lensing affects our view of the universe. By studying the distortions, astronomers gain knowledge about the matter in the galaxy cluster responsible for the lensing, including both visible and dark matter. This discovery is a milestone in understanding how light behaves under extreme gravitational forces and helps scientists verify Einstein's theories about gravity and light. This breakthrough opens doors for further astronomical research. JWST's ability to capture these detailed images means we can explore more cosmic phenomena affected by gravitational lensing. Future supernova discovered this way may reveal even more about the distant universe, the distribution of dark matter, and the behavior of light across vast distances. As JWST continues to observe distant galaxies, astronomers hope to uncover more mysteries of the cosmos, pushing the boundaries of our understanding of the universe and how it evolved. Supernovae are among the most spectacular and energetic events in the universe. They occur when a star exhausts its nuclear fuel, causing its core to collapse, and the outer layers of the star to explode. This explosion releases a vast amount of energy, outshining entire galaxies for a brief period. The remnants of a supernova can form neutron stars or black holes, while the expelled material contributes to the creation of new stars and planets. Understanding how supernova work is crucial for comprehending the life cycles of stars and the broader cosmic ecosystem. Gravitational lensing has been one of the most powerful tools in modern astronomy. It allows us to observe distant objects that would be too far away or faint to see otherwise. When light from a distant star or galaxy passes through the gravitational field of a massive object, like a galaxy cluster, it bends and distorts. By analyzing these distortions, astronomers can study objects that are located billions of light years away, providing new insights into the structure of the universe, including the nature of dark matter and dark energy. Dark matter plays a significant role in gravitational lensing. It is an invisible form of matter that doesn't emit, absorb, or reflect light, but its presence can be detected through its gravitational effects. In galaxy clusters, dark matter forms a massive gravitational well that bends the light of objects behind it. By studying how the light from distant supernovae is distorted by dark matter, astronomers can learn more about this mysterious substance, which makes up roughly 27% of the universe's mass energy content. One of JWST's most groundbreaking features is its ability to observe the universe in infrared. Unlike optical telescopes, which observe visible light, infrared telescopes can see through cosmic dust and observe faint objects in distant galaxies. This allows JWST to capture phenomena like supernova Y and gravitational lensing with unmatched clarity. JWST's infrared technology provides astronomers with more precise data, enabling them to study objects that were previously invisible or distorted by cosmic interference. While Hubble was a revolutionary telescope, JWST takes things to the next level. Hubble's observations were limited by its optical focus, and while it did capture some gravitationally lensed objects, it struggled to resolve finer details. JWST, on the other hand, is specifically designed to study distant and faint objects with greater accuracy. Its higher resolution and infrared capabilities give it a distinct advantage, making it the perfect tool for unraveling the mysteries of supernovae, gravitational lenses, and other cosmic phenomena. The discovery of a supernova distorted by a gravitational lens is a milestone because it provides new insights into two fundamental aspects of space: the nature of supernova and the behavior of light in extreme gravitational fields. This discovery also helps bridge gaps between theoretical predictions and observational data. For astronomers, this breakthrough opens up a new realm of possibilities for studying the universe, offering a clearer view of phenomena that were previously too distant or complex to understand. Welcome to Blessovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blisovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe, live Q, and sessions with experts. Your membership will grant you the chance to participate in live Q and sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blisovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment.